We are going over the lab. Did you turn it in? All right, so let's do.
Erin turned hers in, but then I misplaced it, so I don't know where it is.
Can you go back on Blackboard and grab it?
I tried, it's not printing out.
Oh no.
So I'll try to just print another copy and go with it, but I don't have our answers.
Okay, so I'm sharing the screen, aren't I?
Yeah.
What you need to do is pause share for a second. What do you see when I do a pause share? Do you just see people's faces?
Just says Zoom.
You're not seeing anything that I'm showing you right now.
No.
Okay. So let me go take a look at your.
Sorry.
Okay, so Lena, Aaron, Tim, Shannon, Isaac, and Zach. Ryan, where's yours, buddy?
I just turned it in like a minute ago.
Oh, wait, never mind. Okay, Ryan, you did do that. All right, so I'm gonna take a look at Ryan's. I'll look. All right, I'm going to share the screen on this in a second. Okay, so Ryan, it's not too bad, okay? From what I see, this is not too bad so far. Okay, so let me go to somebody else's. Who is proud of the work they did?
Me.
Tim?
Yeah, sure.
Okay. Let me see what Tim's got here. Okay, I'm gonna resume share. So now you're looking at Tim's stuff, right? Okay. So when we do these things about scientific notation, right, the thing that you need to keep in mind is, what color do I feel like? What color do you like to watch? Which of these colors is nicest for you?
I don't know any of those colors.
Blue.
Let's go to the dark blue. I kind of like the dark blue. I like dark blue and dark green. So
Can you make that bigger?
Well, I'm going to draw it right here.
Okay.
Okay. So 2 hectometers, right? And what that means is the unit, which we said is the what, is a meter. So meter is the unit. Hecto is a prefix. And according to this, hecto means 10 squared. So what you do is you substitute this. Now, is that in scientific notation? So Tim, what I would say that I'm going to look for when I finally grade your stuff is I need to see meters in here.
All right.
Because that's the value includes the unit. So all of these should end up in meters. But it is 2 times 10 squared because that is scientific notation. Now, this next one, let's look at 40 megameters. So what I'm going to do is I'm going to rewrite the mega with 10 to the 6th meters. Now, is this in scientific notation? And the answer is no. So what is 40? 40 is 4 times 10 to the 1st times 10 to the 6th meters. So what I'm really asking you guys to do is to be aware of this yellow is becoming that. This is staying the same, which is this. And then in all of these, the meters stays the meters. Now, when you finally do this at the end, you have 4 times 10 to the 7th meters. Because I can, when I multiply exponents, I'm adding. And we do have 4 times 10 to the 7th meters. So Tim and others, you may have just written that down, and that's fine. But I want to make sure that you don't do something stupid and show it in nice, neat, original order. Now, by the way, Ryan, just so you can see, I think that typing it out is a good thing. Because it's neater, especially if you don't have neat handwriting. Lena, her handwriting is like printing. It's amazing, but mine would suck. I wouldn't want to accept my handwriting, and my handwriting is not as bad as some of yours. Okay, next one, same three, same thing. Now, again, I don't know offhand if this is right. So I go 325 nanometers, and I'm going to go, that's 3.25 times 10 squared times nano. What's nano mean? If you look in there, it's to the -9th time meters. So again, keeping in mind what I'm doing is 325 is 3.25 times 100, or times 10 squared. Then, nano means times 10 to the -9th, and meters is a meter. So I put them all together, and I get 3.25 times 10 to the -7 meters. Now, this is what he has, minus the meters. So he got that right. But what if he got this wrong? What if he said 10 to the 7th? What am I supposed to do with that? If you did something stupid here, I could find where you made the small mistake and give you partial credit. Just a thought. All right, 1.8 times 10 to the -5th. Oops, sorry. 18 micrometers. So this is Greek letter, mu, right? That little letter here is mu. Mu is like a French cat. And what we're going to say is that this is 1.8 times 10 to the 1st times 10 to the -6th meters. And again, 18 is 1.8 times 10 to the 1st. Micro is times 10 to the -6th. And meters is the unit. And then when all of these are together, I get 1.8 times 10 to the -5 meters. Micrometer, by the way, is going to be the one that we're going to use most often for radiation. If it's a micrometer, sometimes people call it a micron. A micron is a micrometer. And, you might say micrometer, or you might say micrometer, just like you might say kilometer or kilometer. Fair enough? Any questions on that? Everybody good?
Yeah.
Okay. When we go over here, now we're talking about a couple of things, and we did want to say something here, that lambda is a wavelength. And a wavelength is the length of one complete wave. Or if you think of a wavelength as being like this, you could say it's the distance between two, what do you call those? What's the top of the wave?
Crest.
You could put crest or peak, but in meteorology, we're not going to call it either. The top of that is going to be called a ridge. That's the word I want you to know, okay? What do you call the bottom?
A trough.
That's going to be a trough. So in meteorology, these are the words that we use for waves. Okay? That's a wavelength. And the unit of wavelength is a meter. However, in radiation, we usually use micrometers because visible light is in the micrometer range. So if you go look at your notes for the bands that we talk about, what is the visible spectrum? What, from where to where? So get out your notes from Unit 3 and tell me what the visible spectrum is. What do you guys have?
It is 0.38 micrometers to 0.75 micrometers.
Now, for years, I did 0.37 to 0.76 micrometers. Is that what's in the notes now? I did some web searching and I couldn't figure out. I'm getting a whole bunch of different numbers. And since I personally haven't gone and experimentally determined what this is, I really don't know what the answer is. So it's about there. Do you agree that the visible spectrum is very narrow? How many colors in the visible spectrum? Well, what are the colors of a rainbow? How many? And what's the initials?
There's 7 colors.
What's the word, Aaron? Remember that person's name that we sometimes pretend? Everybody else, what is it? Say it.
Aaron says RGB.
Well, no. You've heard this before, everybody?
No.
Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Have you heard that? You've never heard that, Lena?
I've heard it before.
Okay, well, there's the 7 colors of the rainbow. So the longest ones are red. The shortest one is violet. So it really goes, it's actually Vib G Yor in terms of going from short wavelengths to longer wavelengths. And notice if what's going to be longer than red is going to be infrared, right? And shorter than violet is ultraviolet, right? So you have to realize that. Now, what does it say in my notes for ultraviolet? How long is ultraviolet radiation?
Around 0.1 micrometer.
Okay, so it should say something like this. And this tilde, do you know what that really means? It means on the order, like order of magnitude. Of 0.1 micrometer. So in other words, it's somewhere in powers of 10, which is power of 10. It's on the order of 0.1 micrometer. Now, what about infrared? Infrared is on the order of 1 to 10 micrometers. And I think we've talked about this. Infrared is a big spectrum. So we have the near infrared, and then the longer ones are the far infrared. And then what's on the order of 100 micrometers? What does it say?
Microwave.
That's what we call microwaves. Now, do you agree that micro usually means small? And that's getting on the bigger side. But that's because on the order of 1,000 or more, that's radio waves. So when we talk about microwaves, these are small radio waves, microwaves. But their microwaves are a lot larger than infrared and visible and ultraviolet. And then what is it on the order of 0.01 micrometers is what?
X-ray.
Those are called X-rays. Are you getting the idea that the smaller the wavelength, the more dangerous it is? Radio waves don't bother you. Microwaves could bother you if you had a lot of water and you put yourself in a microwave, your water will start to boil. Infrared makes you warm. Visible light, which is very small in between, visible light makes you see. Ultraviolet light gives you sunburn. X-rays see your bones. and cause problems if you have too much of them. And then what's the smallest one? 0.001? Those are gamma. And what do gamma waves cause?
Cancer.
Well, they could, but they also turn you what color?
Green.
And they turn you green and you get really big and you start beating up things, right?
Like the Hulk, yeah.
Like the Hulk, right? That's gamma rays coming in here. So that's that. Anyway, that's silly. But that's what the spectrum is. And you should know something about the spectrum. So we're basically measuring the spectrum in terms of wavelength. But we have this equation. We also have something known as frequency. And I'm going to use F for frequency. And the number of waves, so if I have a wave going up and down, it's like this. That's a frequency. And the unit of frequency is like beats per second or waves per second. But you see, a wave or a beat is not a unit. These are not units. So the only unit is actually a per second. Now remember, this is how you write 1/seconds, per seconds, which is the same thing as per seconds. So what that tells me is that this is the unit of frequency. That's the unit for frequency, a per second. But people don't like to say per second. So I could say, well, the frequency is 38 per second. People don't like to do this, so they call this a hertz. Because that's what we call it. But what is a hertz actually? It's a per second. Does that make sense? That's what it is. Okay, now, there's a relationship that says lambda times frequency, wavelength times frequency, is going to equal to C. What is C? C is something known as the propagation speed. Propagation speed. It's how fast does this light travel? And when I say light, see, we often say the word light when we really mean what? Electromagnetic radiation. We call it light, but we mean electromagnetic radiation. Because light, do you agree that infrared is light? And microwaves are light. And radio waves are light. It doesn't make sense to call it a radio wave because we often think visible light, which is visible spectrum electromagnetic radiation. So we're really talking about EM radiation. People get confused because they hear about radiation and they think, oh, isn't that dangerous? But that's not what we're talking about. Radioactive and radiation are different. Radiation, if it's really shortwave, can be dangerous to you, but obviously long wave radiation is not a problem to you. Anyway, so I have lambda times F equals C. And then I wrote it here. I'm like, well, I could lambda equals C over F. And so what we have is A equals B over C. Now in this equation, I asked, what is the relationship between wavelength and frequency? And what's the answer that you're going to give me? To what?
Frequency.
If
C is constant. And C is always constant, right?
And here's the thing, right? This is a true statement. So that means long wavelengths will have long wavelength has a small or a low frequency. Right? So when we did spectrum, 0.37 to 0.75 micrometers, this is violet. Violet has a higher frequency than red because the shorter the wavelength, the higher the frequency. So a lot of times people will refer to the electromagnetic spectrum not in terms of wavelength, but in terms of frequency. So longer waves in the radio spectrum have lower frequencies. Longer waves, lower frequency. In television, we have these terms. You know what that stands for? UHF and VHF? Are you familiar with these terms?
Isn't VHF, was it very high frequency or no?
Very high frequency. What's UHF? What's more than very?
Ultra.
Ultra high frequency. You know, you can talk about radio, which is HF. These are longer wavelengths. And then you have LF, low frequency, really big wavelengths. So anyway, we're talking about that. And you have FM and AM. Do you know what AM and FM stand for? For radio?
No.
FM stands for frequency modulation. AM stands for amplitude modulation. So when I have a wave, that is the amplitude is the distance from a center line to the crest or to the trough. So this is a higher amplitude than this.
I have a question.
Yes?
Isn't it on AM, like if there's lightning, then it gets staticky? Is there a reason why that is?
Well, yes, there's a reason.
Yeah.
You want me to tell you what the reason is?
Yes.
I'd have to shoot you. No, I don't. It probably has to do with, I don't know. I don't know what it is.
Yeah.
Oh,
Is
really?
it specifically AM?
Why lightning causes AM static?
Is it specifically AM that it affects?
Yes. More than anything. A lightning strike is like a radio transmitter producing radio waves known as spherets that cause the familiar static we hear. Charles Moore, lightning expert at New Mexico Tech, and Bill Wontraba explained that lightning generates a broad spectrum of radio frequencies peaking at about 10 kilohertz. Kilo is to the third, so 1,000 waves per second. The power emitted by a radio wave decreases rapidly as the frequency increases. So the power received from a lightning strike at the low end of the AM dial is about 10 times stronger than in the received at the high end. For this reason, static is considerably more noticeable at the low end of the AM band. Higher frequencies like FM are affected even less. So AM, like I listen to WGN radio. If you listen to WGN radio, do you know what the station WGN is? WGN is 720 kilohertz. If I were listening to FM radio, what FM radio station do you listen to? Is there even one that you listen to? How many of you listen to FM radio ever?
If the Bluetooth is acting up in the car, yeah.
Right? I got Bluetooth. I use my phone, or I have Sirius XM, because then I don't have to worry about commercials. I hardly ever listen to radio. What do you listen to, Zach?
I can't exactly remember, but I think one is like 1003.5 or something.
103.5, yeah, 103.5. I think that's, is that, no, Blaze, no. But those are megahertz. So mega is 10 to the 6th, kilo is 10 to the 3rd. So these are way higher frequencies than this one is. And the lower the frequencies, the more they show up. So if I get AM radio, let's see. I'm going to see if I can do this. This would be cool. You can hear that. This is way too long. Give me something short. No, I don't want 10. Yeah, this is a little bit shorter.
So I got out the AM radio receiver that I had to build for my amateur radio intermediate license, and I turned it on during one of these storms. Whenever there's a lightning flash, you hear it over the radio at the same time as you see the flash. You can also use this to listen to storms that are too far away to be seen. If you want to try this yourself, then tune to the lowest frequency that you can and just listen.
There is something known as a zipper effect. And I'm not exactly sure what causes that, but it is called spherics. That's interesting. You could do that with television, but a zipper effect, sometimes you hear the and you'll hear the lightning. So the zipper is when the sky is starting to ionize before the lightning hits, and then the static discharge comes up, but you'll hear this. It's a zipper. It's what we call a zipper effect. And you know, when we used to go out storm chasing, we'd have the radios on before we had cell phones and all this stuff, and we'd have AM radio, and we'd listen to it all the time just to hear the amount of lightning coming up. We try to figure out, is this storm starting to produce lightning? And we would actually listen to that. So
That's pretty cool.
that's kind of a fun thing. Sorry, that was a complete switch. Do you mind talking about weird stuff like that? That's kind of geeky science, right? Now you know. So what were we talking about? We're talking about amplitude. So amplitude of a wave is really not that important, but of other things like water waves or sound waves, amplitude refers to what? What does that tell me about the wave, the amplitude? Anybody know the word that I'm looking for? Anyone? Bueller?
You have something? Hello?
Did Aaron get it?
She's saying something, ST, how strong it is? She says how strong it is.
Okay, and the word is power, right? So the amplitude refers to power. It's basically how strong it is, right? So when you have these high amplitude water waves, there's a lot of power in them. If you're talking about sound waves and you want to increase the power of a sound, what do you plug it into?
An amp.
An amplifier, right? An amplifier is increasing the amplitude. So that's what it means. In electromagnetic radiation, we're not going to worry about amplitude, at least for anything that we do in this class, okay? But we do have this equation, right? C over F. And we know that long wavelengths, short, they're inversely proportional. But what's the relationship between those two? And I've already given you this as sort of the stuff in here. And there is no relationship. And why is that? Because the speed of the wave traveling through space, the propagation speed, is constant. And it's always constant. And we call that the speed of light. And the speed of light is 186,000 miles per second, or in metric, 3 times 10 to the 8th meters per second. So this number here, 3 times 10 to the 8th meters per second, is always going to be the case, And you always need to know that, okay? That is just going to be the case. So that's the only number you need to worry about. Okay, any questions up to that point? Did you put these into scientific notation? I think I skipped past this, didn't I? Did you have any problems with this, anybody? So watch, 51580. You're basically saying you're making it 1, 2, 3, 4 times smaller, which means the 10 has to get 4 times bigger. 5.158 times 10 to the 4th. Doesn't matter if you have the 0 in there. I'm not going to care about that. Zach, what's your major?
Going for like game design and development.
Okay, has anybody ever taken the chemistry or physics?
In high school.
Yeah.
Yeah, they used to use significant digits.
Big figs.
And you know what's stupid about it is that you use significant digits before you do anything, which is the lamest time to do it. Don't worry about it. Eventually, it'll make sense to you. Anyway, these are all correct. Although, no, they're not. What's wrong with this?
Oh,
It needs to be 1.028
yeah, times.
10 to the, well, don't forget that 1028 times 10 to the 5th is 1.028 times 10 to the 3rd times 10 to the 5th, right? So this becomes this becomes that. And now it's 1.028 times 10 to the 8th. And the same is true with this one here. So fix that. Do you guys have any problem with anything up to the final solutions for these problems here? All right, now on this one, you know, you go to the old handwriting, which is fine. What I like about this, and this is what I will look for, is I want to see the steps. That's a good way to do that. So let's just, and this is true of any problem solving. What's the first step? The first step is write down the equation that pertains to the problem at hand. So you write this equation because that is the relationship between wavelength, frequency, and the speed, propagation speed. Write down what you know in scientific notation. So I've given you one here. I'm going to go ahead and look at the next one, which is frequency is 20 kilohertz. So over here, oops. Frequency, that never ceases to make me laugh, equals 20 kilohertz. And what you do is you go frequency is 20 times 10 to the 3rd s to the minus 1. Keeping in mind that a hertz is a per second, kilo means times 10 to the 3rd, and 20 is 20, but I go in here and I go frequency is equal to 2.0 times 10 to the 1st times 10 to the 3rd, s to the minus 1, and then I go frequency is 2.0 times 10 to the 4th, s to the minus 1. This is what you have been given in scientific notation. So I should see that step. I should see the working out of this, and then maybe, you know, if you want to do things right, then say, oh, okay, circle it, or put a box around it. Go, there's one. But what else do you know in scientific notation? You also know C equals 3.0 times 10 to the 8th meters per second. So step 1, step 2. Now step 3, what is step 3? isolate the unknown. So which of these is unknown? Well, I know F, I know C. The only one that's that is lambda. So I'm going to go and say step 3 is lambda is equal to C over F. Make sense? Now, it's only in step 4 that you plug in. If I see you, listen to me, if I see you plugging in before step 4, I'm going to mark you wrong. Does everybody understand that I'm saying that? Sam, you paying attention?
Yes.
So lambda equals C over F, and then I plug it in. So I go 3 times 10 to the 8th meters per second divided by 2.0 times 10 to the 4th per second. Then I solve. Best way to do this, in my opinion, is to create cancellation. So what's in the numerator and the denominator? S to the minus 1 goes away. What am I left with? Meters. Isn't that what I want? So I'm happy. Now, last time I checked, 3 divided by 2 is how much?
1.5.
1.5. 10 to the 8th divided by 10 to the 4th. When you divide exponents, you subtract times 10 to the 4th meters. And then I look at this and I go, oh, well, hold on a sec. That seems to be good. I don't even need to do anything with that, do I? And that's the correct answer. So what that says to me is this. So listen carefully. When I have an electromagnetic wave with a frequency of 20 kilohertz, that wave will have a wavelength of 1.4 times 10 to the 4th meters. That's 15,000 meters. That's a big wave, 15,000 meters across with the 20 kilohertz. Now, I'm going to do another one. Anybody have questions on that?
I have a question.
Yes, go ahead, Isaac.
So for the letter C, I think I'm a little confused. Is C the same for every question?
Yes. So what that says is that radiation travels through space, and that technically that's the speed of light in a vacuum. That's
Okay.
the technical thing. So space is a vacuum. And what we're saying is that it doesn't matter what the wavelength is. If it's electromagnetic radiation, it will all travel at 3 times 10 to the 8th meters per second. Always. Infrared, ultraviolet, gamma rays, X-rays, whatever. They're all traveling the same speed. Now,
Okay.
when they go into a different density, they do change their speed a little bit. That's why it bends. But I'm not going to worry about that for this section, okay?
Okay, thank you.
So that number is always that. You will never be confused. That's why there's no relationship, because relationships only work direct or inversely proportional if it's a variable. C is not a variable that you need to worry about. So let's just do this next one. And I'm going to go, okay, write down the equation, lambda times F equals C. That's one. Write down what I know in scientific notation. I know that C is equal to 3 times 10 to the 8th meters per second. And I know that wavelength is 900 millimeters. But I know that 900 is 9.00 times 10 squared. 10 squared times 10 to the minus 3 meters. So keep in mind, meters is a meter. Milli is times 10 to the minus 2, and 900 milli is times 10 to the minus 3, and 900 is 9 times 0.0 times 10 squared. Right. So again, I just want you to see the relationship between all of these guys. And what that says is that the wavelength is now equal to 9 times 10 to the minus 1 meters. Then you isolate the unknown. I know lambda, I know c, I don't know f. F equals c over lambda. Now I plug in 3 times 10 to the 8th meters per second divided by 9 times 10 to the 1st meters. First thing I do is I look in the units, meters cancel. I'm left per seconds. And that means I'm frequency. Now 3 divided by 9 is 0.33 times 10 to the 8th divided by 10 to the 1st, which is 10 to the 7th per second.
Isn't it negative 9 times 10 to the negative first?
I'm sorry, Tim?
Isn't it 9 times 10 to the negative first, not 9 times 10 to the first?
Yes, sir. 10 to the minus first. Yeah, right, minus 1. So that, see that, there's a stupid mistake. And it's easy to make stupid mistakes. But if you do all the work, I could say, oh, you just blew that. So yes. So 10 to the 8th divided by 10 to the 7th is 10 to the 9th. So this is saying that the frequency is 0.33 times 10 to the 9th per second. Is
I
this
put-
scientific notation?
No.
So I need to go 3.3. And do you understand that I'm making this number bigger, which means this number gets smaller? Times 10 to the 8th, s to the minus 1. And that is the answer in scientific notation. And you don't have to convert to megahertz. You could say 330 megahertz, which is true, but this is a good, acceptable answer. Everybody good with that? And you're going to need to do that with this one. Because again, you should be able to figure that out. Do you have any questions about any of these things? Can you show me that work nice and neatly? Does anybody have a problem getting to the answer? Because if not, we're done with this lab. Okay. All right, so now we can go back to our lecture. And we had this the other day. And what is this called?
Was it Planck's black body distribution?
And what's this axis labeled?
E star.
And what does E star stand for?
The energy
Yes.
flux?
There's a name for it though.
The radiance.
E star is irradiance. It is an energy flux. It is watts per meter squared. It is the rate of energy flowing through a surface per square meter. This is wavelength. And we have a graph that, again, it's supposed to look something more like this. What do we know about the axes of this graph?
They are infinite.
Say what, Shannon?
They're infinite.
Okay, they go infinitely long. And what else is the axis? Besides infinite both ways?
Asymptotic.
Well, it is asymptotic, that is true, because it never quite goes to zero either way. Gets close, but it never gets there, but it's also logarithmic. And it never goes to zero because you can't have a wavelength of zero. But you can have an infinitely long wavelength, I suppose. And the area underneath the curve represents what? What does the area underneath the curve represent?
Is it a finite area?
It is a finite area, and it represents what?
Is it-
Isaac, what do you say?
Um, sorry, the volume was a little quiet. Could you repeat that?
What does the area represent?
The area,
Zach, what do you have?
I'm looking at my notes and I don't see anything about area. I don't know if we went over that or not. I know we went over that the area is finite. and
Okay. Well, what is it? What is it supposed to represent? Anybody?
It's
Right? It's the total energy that's emitted by a black body. The area represents the total energy emitted by a black body. Now, do you remember we did this the other day? We set up this fraction. And we calculated what was the answer to this problem. What did we get?
It was 16 times 10 to the fourth.
Yeah, well, let's just do it this way. That might be easier just for the sake of knowing. 160,000, right? Which is really 1.6 times 10 to the fifth in scientific notation, but 160,000. So what we said is the sun radiates at a rate, right? This is a rate of energy. It radiates at a rate 160,000 times more than the Earth. So if I were to give you this black body as the sun, and then I show you one as the Earth, the sun, if I use the same graphs, would be 160,000 times more energy, would be 160,000 times bigger area. When you look at some things in the book, they call it normalized. Normalized means I'm not worried about the size being different, but the reality is the size would be different. This would be 160,000 times, and the Earth would be like this little squiggle up down there. If you did it right. Fair enough? And we know that that total energy is proportional to the absolute temperature taken to the fourth power. Hotter objects emit more radiation. Does that make sense to you? Say yes or no. Hotter objects emit more radiation.
yes.
But an object that's 2 times hotter will give off 16 times more energy. How many times hotter is the sun than the Earth?
20.
And the answer is 20. Doesn't seem like a big number, but when you look at how much energy it's radiating per unit area, it's 160,000 times more. And then when we look at how much bigger it is, we came up with some incredibly huge number more radiation. That's what we did Tuesday. Any problems on that? Okay.
What's that equation? E, the one above there? Yeah, what is that?
R equals sigma, that's Greek letter sigma, T to the fourth. So sigma. Then what do you call this? What is the
Is it
name of
the
this equation?
Stefan-Boltzmann
That's
law?
the Stefan-Boltzmann law. I think we wrote that down the other day, right? It's definitely in the work in the notes.
Okay.
Okay. Now, there's one other thing in here that's interesting. And I'm going to show you on this graph right here. Hey guys, what is a graph anyway? It's a bunch of what? A graph is really a bunch of what?
Ordered pairs.
Okay, that's way too sophisticated. Ordered pairs, that's the second answer. I was going to say points, but you said ordered pairs, right? So what I'm saying is that every point on this graph says at this wavelength, this much energy is coming out. In other words, remember how I drew that little thing and I said the different wavelengths coming out? Each wavelength will have some amount of energy radiated at that wavelength. That's what this is. This point says, at that wavelength, how much radiation? What's the rate of energy coming out at that point? This one, we're going to call lambda max. Because at this wavelength, whatever that wavelength lambda is, it's giving off more energy at that wavelength than any other wavelength, right? This wavelength is responsible for more energy than any other wavelength. Do you understand what I'm saying? There is an equation that governs this. And it says that lambda max is 2898 divided by temperature, and the unit given will be micrometers. This is called Wein's displacement law. So W's in Germanic language is the V sound, so this is Wein's displacement law. Do you agree that this looks like A equals B over C? So what's the relationship between lambda max and temperature?
Inversely proportional.
Okay, so say that. Full sentence, Zach.
Lambda max is inversely proportional to T as long as 2,898 is constant. Which
Well, and it is, right? So that number is a constant. Now, two things. First of all, this is a constant. Do you see that this, what is this over here? That's a constant. We didn't need that constant because when I put it into this comparison,
Ratio, fraction.
Fraction.
you all should be saying that. Aaron, you too. Comparison, ratio, fraction. So scream it out, Aaron. Everybody should be saying it. When I was in that, when I was in this equation, whatever was in the numerator, sigma, was also in the denominator, and I canceled it out. So I could have said this. I could have said lambda max is a constant over temperature. But I didn't. I gave you a specific number, and you'll see why I gave you that number. Second question is, what do I know about the temperature? What kind of temperature?
What are you trying to say?
What kind of temperature? Shannon?
Would it be the temperature from the sun?
No, you're missing the idea. What kind
Oh.
of,
Oh, would it be radiation temperature?
no,
It's the absolute term.
Oh,
it's
the absolute.
absolute temperature.
It
The
is-
absolute temperature is Kelvin. So we want to put that into kelvins. Okay, so let's do this for a second. I'm going to rewrite this. And I'm not worried about the unit because I know the unit's in micrometers. So what is the temperature of the Earth? I would go 2898. What is the Kelvin temperature of the Earth?
200.
So lambda max of the Earth is what? What's 2898 divided by 288? You should be able to recognize that. It's really close to what?
It's about 10.
10 micrometers. Now, what's lambda max of the sun? You could plug this in. Remember what temperature the sun is? You could put it in there and you'd get something. But how much warmer is the sun than the Earth?
20 times.
If it's 20 times warmer, then lambda max would be 20 times smaller. What's 20 times smaller than 10 micrometers? 0.5 micrometers. Are you following me? Isaac, are you following me?
I was just finishing writing it down, but I think I'm a little confused from where the 0.5 came from.
Ryan, explain that to him, would you?
So the Earth is, or the sun is 20 times warmer than the Earth, and what is it? So the max wavelength is equal to 2,898 divided by the temperature. So since we know that the temperature of the sun is going to be about 20 times greater than the temperature of the Earth, we can also tell that the max wavelength of the sun is going to be 20 times less than the max wavelength of the Earth.
Okay, that was nice job, Ryan. So, Isaac, did you follow that? Because you can say no, I'm okay.
No, I didn't.
Do you agree that this is the equation? This is Wien's displacement law.
Yeah.
What's the relationship between lambda max and temperature?
They are no temperature.
Right? A equals B over C, right? A and C are
Yeah.
what?
Well, isn't C constant?
Well, no. Because remember, this is A equals B over C. Right? So B is constant. C is the denominator. C is temperature.
So they're inversely proportional.
Inversely. So do you agree that hotter objects are going to give off shorter wavelengths?
Yeah.
Okay. Sun is 20 times hotter. So how much shorter will it be? 20 times shorter, right? 20 times longer, 20 times, so I'm sorry, 20 times hotter, 20 times shorter.
Okay.
10 divided by 20 is a half,
Okay, that makes sense.
okay? Everybody good with that then? I just want to make sure. Sam, you good with that?
Yep.
Okay. In any event, what kind of radiation is 10 micrometer? You wrote down the electromagnetic spectrum. What kind of radiation is 10 micrometers?
Infrared.
Right? And we said infrared was on the order of 0.1 to, or 1, sorry, 1 to 10. So since it's on the large side, wouldn't that be far infrared? Long wave, terrestrial radiation. What is 0.5? Radiation is 0.5.
Could that be visible?
Where in the visible spectrum? Isn't it right smack dab in the middle of visible light? You know what kind it is? It's actually green. At least at 0.5 micrometers. But isn't that what we said with the Earth and the greenhouse effect and the sun? The sun gives off visible light because it's radiating as a black body at almost 6,000 Kelvin. It goes through the atmosphere. It's transparent. The ground absorbs it, gives off different types of radiation. It's giving off radiation based on its temperature being 288. That's why the greenhouse effect works. Kind of convenient, isn't it? Because this is how radiation works. Now, this is Wien's, here's Planck's black body curve. Let me draw another one. So this is black body B. This is black body A. Do you agree that lambda max of A is like that? Lambda max of B is like this. This wavelength is much larger than this wavelength, isn't it? So what do you know about temperature of A versus the temperature of black body B?
Is the temperature of A warmer?
Temperature of A is warmer than B because lambda max is shorter wavelengths. Now, technically, watch this. Do you ever just watch for a second? Technically, it should look like this. Because this body will be a lot at colder temperatures will give off less radiation. The area underneath would be less. So the shorter the wavelength, not only is it over here, it's also much larger area. But if they're the same area, then we say that this is normalized, so that we're not worried about that difference. Now, oops. Let me look here for a second at a cigarette lighter. Image of a cigarette lighter. See the flame? The flame is orange up there. Here the flame's blue. Which is hotter, and how do you know? Lena?
Well, I
Um,
know I've been told that like white fire is the hottest.
Well, not really.
mm,
And I've been told wrong.
so based on like radiation stuff, wouldn't the blue be hottest because it has a longer radiation wavelength in
No, wait.
comparison?
Hotter objects would have shorter wavelengths, right?
Yeah. Right.
Blue is shorter than orange.
Yeah.
Roy G. Biv, right? So because it's blue, it's a shorter wavelength, means hotter temperature. So here's the thing, Lena, because what you said, that is not true that white is hotter. But here's an idea. Imagine that you walk into a room, and in this room is a large heap of metal that's really hot. Okay? If I looked at its black body curve, and it's really warm, it's going to look like this. Something like that, right? And that lambda max might be infrared. Turn off all the lights. Do you know where the metal is? How do you know that, Ryan? How would you know where the metal is if all the lights were on?
It would probably, if it's like really hot, it might melt, or.
Well, you don't know if it's melting. You can't see it. Would you know where it is?
You
And the answer is
give off any visible light.
no visible light.
Oh, you could feel the heat.
Yeah, wouldn't you walk in and go, ooh, I can feel it hot in there. When you walk into something like a radiator, you go, I can feel the heat coming from that. You close your eyes, and you know where the fire is, right? You're not going, oh, the fire's it's warm in the room. No, the fire's over here. I can say that I'm getting the heat from the fire. So that big piece of metal is hot. And I can feel infrared radiation coming to it. But let's say that this hunk of metal starts getting warmer. What happens to the black body curve? Two things. What happens? Tim, what do you say?
I'm thinking real quick. Not sure.
What do you say, Zach?
Would the area increase?
Okay, the area underneath it would increase because it's warmer. And what would lambda max do?
It would increase as well. Like it will shift to the left, so it's a
It'll
shorter wavelength.
shift to the left, right? It'll look more like this, won't it? Now lambda max is at shorter wavelengths. So that's why it's called Wien's displacement law. The curve gets displaced to the left for shorter wavelengths. Now, what if lambda max was like at 0.8 micrometers? Here's the thing I want you to understand. Is lambda max visible yet? No. But is there some radiation being emitted in the visible spectrum? And the answer is yes. Some of it is. The lambda max is not, but there's some. Remember, a black body gives off all types of radiation. Well, what's the first type of radiation that would be visible? What color? Wouldn't it be red? That's the longest wavelength. So what would now you walk into a dark room and the metal's hotter. Isn't it going to glow red? If it gets warmer, what color will it start to glow? Orange. What if it gets really hot? Well, do you agree that if it's really hot, it's going to give off red light? Red would be here, and it's going to give off blue light and green light. Do you understand it's giving off all the different colors of light? So what color do you say it glows? It glows white hot. Does that make sense? So white hot is way hotter than red hot. You have coals, you burn coals in a barbecue, starts glowing orange, ooh, hot. Starts glowing white, even hotter. But this is glowing what color? Now it's getting blue, which means it's even hotter. So when you have gas, and what kind of gas is this? What kind of gas is in here?
Is it lighter fluid?
What is that?
The propane.
Like you often will. So I don't. Is this propane or no? I think in a lighter they call it butane.
Oh, butane. Yeah.
But you have propane, right? What color? When you have propane gas grill, what color is the flame? It's blue, isn't it? Propane burns really hot. Okay, so imagine that somebody is using an acetylene torch. They're doing welding. What color is that flame? Isn't it blue? That's a really hot flame. Do you agree? Really hot. Much more than if you burn paper, which is burning orange and red. What else do you need to have what other piece of equipment do you need if you're using an acetylene torch?
You need like a helmet that has like a special shield because it burns so bright it can like blind you.
It doesn't burn bright. What's it giving off?
Heat.
No, shorter than visible light.
Oh, infrared. Yeah, it's giving off, the
No,
wavelength.
shorter than visible light. Shannon, you're thinking right. You're just backwards. What's shorter than visible light?
Infrared.
No, that's longer.
Microwave.
No,
UV,
still
UV.
ultraviolet radiation. What does ultraviolet radiation do? Gives you suntan. So if you're using an acetylene torch, you're giving ultraviolet radiation. Have you ever heard stories of people who go to a tanning booth and they keep their eyes open? You're supposed to wear those little goggles, and there's people who keep their eyes open. Why? Because it's not bright. It's just this soft, palish light. But ultraviolet radiation is burning your eyes. It's like getting sunburn on your eyes, really bad sunburn on your eyes. And people have done really bad things to their eyes by keeping them open. So if you have a acetylene torch, you're getting ultraviolet radiation. So not only do you have to wear goggles because you're stopping ultraviolet radiation, what else do people often get? They get suntan. Anybody who works with these torches has to wear long, big gloves, long sleeve shirts because they're getting suntan. They're exposed to ultraviolet radiation. When I look at the sun is burning hot. Do you agree that I've got all different colors of light? That's why we call it white. That's because lambda max is right there in the middle of the spectrum. If the sun were hotter, what color would the sun become?
Doesn't it become blue?
It would become blue. So what's the hottest? Blue hot is the hottest. So red hot is hot, white hot's hotter, but what's hotter than that? Blue hot.
That mean that blue lightning is the hottest?
I would think so.
Is that why some planets burn blue?
I mean, stars?
Stars, not planets.
Yeah, yeah. Yeah, because they're just warmer. Our sun is more of a yellow star. Yellow star is shifted, the lambda max is shifted toward longer wavelengths. And that's why it is this way. So let me show you something here.
And here's the thing about fire. You can also change the color of it by feeding the fire whatever different chemicals as
Well,
well.
yes,
So,
it's more than that. If just a pure flame and temperature would be different. But
right.
Here's the thing. If you ever work with photography, you look at your camera and you set a light setting and you're giving it it's what they call the Kelvin temperature. It's really a black body temperature. When I have if you've ever taken pictures of people, like individual portraits inside, you want them to be an incandescent light. You would say lights that are yellow are warm lights. What do you call a light that's ugly? Like fluorescent lights. That's because their black body temperature is blue. Fluorescent lights or halogen lights tend to be on the blue side. They're hot. Incandescent light bulbs tend to go to the yellow, and yellow is a much better thing because what's the best light color to take pictures of for people? When do they look the best? When they're outdoors. And what color is the sun? It's yellowish. Why is it yellow? Because I'm removing the blue light through the sky. At sunset, I start getting orange light because I'm removing more and more of the light, which we'll talk about later on. But sunlight is a much better natural field. People look healthy when they're in the sun. If you put them in a room with fluorescent lights, you don't look very good. So just so you understand that. So here's your curve. The curve looks something like this. And what I'm going to do is if this is the sun, let's imagine this is for the sun. Point 0.37, 0.76, whatever the numbers are, micrometers. What does this range represent?
Visible light.
That's the visible light. Do you agree that there's an area underneath this curve? If the entire area is the total amount of radiation, what's the area in here? It's the percentage, or in other words, part of the total radiation emitted in what wavelengths? In the visible spectrum. And the body is such that this for the sun is around 43%, which we've already told you about. What's the next one? The next one is over here. So let's use a different color. Here's the next one. This is what we call near infrared. Near infrared is around 37%. This would be what spectrum?
UV.
And we said how much UV? About 7%. So 43 and 750, 87%. That leaves some out here in the far infrared and over here in the X-rays, gamma rays, right? Little bits. But what happens to most of the X-rays and most of the long waves, especially the short waves? It's absorbed by gases, isn't it? So now we can do something interesting like this. I'll go to the sun's black body curve, and we get something like this. Oh, that's in Italian. Let's see if we can get something that's not in Italian. Well, this is not bad that I look at this one. That's the sun's black body curve. Right, there's the sun's black body curve because the sun's around 6,000. So there it is. And it says right there in the middle, around 500 nanometers, which is around 0.5 micrometers. Because this is 0.5 times 10 to the minus 6th meters, which is 5 times 10 to the minus 7th meters. That's scientific notation. 500 nanometers. Nanometers is 5 times 10 squared times 10 to the minus 9th, which is equal to 5 times 10 to the minus 7th meters. Same thing. So here they're using nanometers. I use micrometers, whatever. And I get the colors of light, Roy G. Biv, colors of the rainbow. And 43% of that area is visible light. If the sun had been warmer, this would have been shifted. We'd get a lot more sunburn because a whole lot more ultraviolet light would be emitted by the sun. If the sun were burning cooler by 1500 degrees, it would be a lot darker in the sky. It would be a lot redder of the sun, and we wouldn't have as much ultraviolet radiation that we need to have, and it would be colder. There's Wein's displacement law. That's what all of these things are meaning. Okay, so here's these curves, and these curves are just equations that we're plotting out. Here. Area underneath the curve is 63 times 76 watts per meter squared. Here's area of the curve, 240 watts per meter squared. Earth, sun, Earth. Notice lambda max is way down here by 10. That's what all these things are talking about here. You know, there's different ways of plotting out the curve, whether the axis is logarithmic or not. By the way, if you want to know what the equation is that you're plotting out, there it is. It's called Boltzmann's constant. They're all dealing with radiation stuff. Now, last thing here, and why?
I have a question.
Yes.
So you know how like the sun looks white to us on Earth?
Uh-huh.
Does it look the same on other planets if you're on the surface? Or is that because of our atmosphere?
Because the sun is centered over the visible spectrum, you're getting very close to equal amounts of green, red, and blue. Reality is you're probably here. Let's do this, paint. So let's edit the color. And I'm getting, let's say for the red, I'm getting 180. The green is going to be more like 210. And the blue might be more like 220. You're kind of the blue stuff along those lines. Okay, so this is the color of the sun. It's maybe a bluish tint. If I were to increase it all to about 200, it gets this color. If they were all equal amounts, then it would be gray of some sort. And that's why we see the sun the way it is. That's the way our eyes are sensitive. Now, here's the cool thing. It's one thing to say that our eyes adapted to the sun because the sun gives off mostly visible light. You could make that argument. But here's what's really cool. Why is it that the sun is giving off the maximum radiation in the visible spectrum, and guess what gases don't absorb? Visible light. It's a pretty amazing thing if you think about it. That the sun is giving off the type of radiation that goes through our atmosphere. If the sun had been colder, what happens? What kind of radiation comes out of the sun?
Near infrared.
It would be near infrared. So what I'm going to do is I'm going to look at, hold on, I'm just having a brain meltdown. Selective absorption. Gases. Okay, and what I want to do is look at this chart here. Okay? And what this is saying, and this is super, super, super important. So luckily you've got this thing. I'm breaking each one of these things into, no, this is, no, I don't want to use this one. You'll understand in a second. This one might be better. Okay. By the way, notice something about this graph. So it's something which we call selective absorbers. The first thing I want to show you is that the bottom axis is logarithmic, right? 0.1, 10, or 1, 10, 100. It's not a linear scale, it's logarithmic. Here is the Earth's lambda max, 10 micrometers. Each one of these strips goes from 0 to 100. So 0% absorption is what?
Transparent.
Transparent. 100% absorption is what? It's totally getting absorbed, right? And it means it's opaque. You're not getting light through it. The bottom strip here is water vapor. Do you see every place where this line goes up here says more and more wavelengths at those wavelengths are being absorbed. So those are all the areas where water vapor does a good job of absorbing. Notice in here, there is a lot of absorption by water vapor. Here, there's a lot of absorption by water vapor. And eventually, water vapor does a lot of absorption over here. What that tells me is that longer wavelengths are absorbed better. Well, when would the Earth give off longer wavelengths?
At nighttime.
Because it would give off longer wavelengths when it's what?
Cooler.
So when it's colder and the Earth is giving off radiation, the wavelengths get longer. Who absorbs it most?
Vapor.
Water vapor. This strip says CO2 absorbs some also. So when it's CO2 absorbing it and it's colder, CO2 does a good job absorbing it when it's cold. So the colder the Earth were to try to get, water vapor, which now keep in mind, right? What did we say about cold temperatures? How much water vapor is in the air when it's cold? The colder it is, how much water vapor can be in the air?
Less.
Less and less. So if the Earth were to get colder, what's going to keep it from getting colder? CO2. Does that make sense to you? Do you see why CO2 is such an important greenhouse gas? It's the reason the Earth doesn't get cold. It does a good job absorbing longer wavelengths, which is what's happening when it's colder. But now let's think about this another way. What if the Earth gets warmer? If the Earth gets warmer, the wavelengths get shorter. Do you see that CO2 does very little absorption? CO2 is why we keep warm, but the warmer it is, the less CO2 is going to do. The warmer the air temperature, the less CO2 has influence. As it turns out, and you probably never hear this, is CO2, in terms of absorption, is what we call almost saturated. In other words, almost all of that CO2 is already absorbing all of it. Adding more, what's that going to do to it? The more and more that we add, the less and less impact CO2 is going to have. That's what that means. Now, let's look at this one. This is O2 and O3. I have a little spike here, and that spike lines up with this. But notice under here, do you see that O3 and O2 absorb almost everything under this wavelength? You see what I'm saying? Almost everything is absorbed except for that. Which tells us what? Ozone and oxygen absorb almost all ultraviolet radiation, except for what? Except for that little blip. That little blip is about 2%. And you remember how we talked about ultraviolet radiation is necessary for us? Don't want to have too much, but we need a little bit. There it is. That's the blip. When I look at all the gases of the atmosphere, I get this top chart. So this top chart here is all the gases of the atmosphere. Do you see areas in here that do not get absorbed? Hardly at all. That's under 1 micron. Where this is called an atmospheric window. And that's defined as a part of the spectrum that is not absorbed.
So even though when it's really clouded out and it gets pretty dark, like during the day, that's only how much the vapor is absorbing?
Okay, no. Hold on. This light down here, which this is visible light, right? That's where the visible spectrum is.
Yeah.
It's not absorbed. What makes it dark during the day?
Clouds. And that's
Clouds are liquid water. They're not absorbing. What are they doing?
reflecting.
They're reflecting. They increase the albedo. So the light's not being absorbed, it's just being reflected. It's like you're just blocking the light. I mean, if you want to use the word block in terms of radiation, clouds block incoming visible light. That just does.
So if this was like showing us how much is reflected, it would be like pretty
That
hot.
would be really hot. Yes.
All right.
But this is what's absorbed. So the atmospheric window is the part that's not absorbed. The visible spectrum is an atmospheric window. Write that down. The visible spectrum is the atmospheric window. Okay, I'm just stretching my legs. But where else is there a big atmospheric window? Isn't there a big atmospheric window right there? Except for what? Except for that little branch right there. You know what this branch is? Oxygen. Oxygen is that little branch. But basically, what's in that red circle is a big atmospheric window. Because ultimately, what has to happen to the Earth's radiation? It has to escape. And what does this do? Sun's radiation gets in. Right? We have windows. The atmosphere is doing a whole bunch of stuff. Good thing is radiation gets through the atmosphere. That's why the Earth can get warm. But radiation's got to get out. We've got to get rid of it. Good thing we have a window to dump radiation out. Inside the window is a window pane. There's the framework. Oxygen is the cause of that one. But for the most part, here's the big window in, here's the big window out.
Yeah, but isn't the window out blocked by CO2?
No, this is blocked by CO2. Wavelengths longer than 10 micrometers.
So the wavelengths that the Earth radiates are not that long.
Well, don't forget, the Earth radiates in the distribution. 10 is the center of that. But less than 10 is over here. There's a big chunk of Earth's coming out less than 10. If it's less than 10, then it gets out. It gets out right here, less than 10. If it's more than 10, what happens to it? It gets absorbed.
So there is still some that gets out.
It's got to.
Yeah.
The point, the kind of the way that you think about it though, is that the warmer something is, the shorter the wavelengths, the more that get out without being absorbed by CO2. So CO2 is limited to how much it really will absorb. It will not be a runaway at that point. Because CO2's main purpose is wavelengths greater than 10. There's a couple places down here it's absorbing it too, but I mean, it acts. These are all things. And the funny thing is, all of these triatomic are doing good at infrared. Diatomic and ozone is going to get good at ultraviolet. This is all absorbed, which is good. And that's why, by the way, when I accidentally did this and I was looking for a graph to show you, and I went to this other one, and I said, oh, wait a second, I can't show you. This was actually a nice graph, except for one thing. Look at the axes. It went from 0 to 100. It's inverse of that. So it's like, oh, that's a weird thing. Why is it backwards? But even looking at this graph, there's your window. That's your window out. This doesn't even go low enough for the window in. So I know there's better graphs elsewhere, but at least the one I showed you is pretty decent. This is a good graph, but I love this, right? That's the one. That's the little blip of 2% that gets in. Isn't that cool? Isn't that kind of funky, the way our planet is? Have you noticed that our planet is really perfect for getting the right kind of light in, and our eyes look at visible light we can see? A couple of things. I like to think about things like this. I think about people, generally speaking, you know, and I think about COVID a lot. And obviously I got COVID from somebody who gave it to me. That's usually the way it works. It didn't just happen. But here's the thing. What kills diseases like that? Answer is ultraviolet. What else does ultraviolet do? It gives you skin stuff, suntan, like skin pigmentations. So what happens if it's a cloudy day and if you laid outside getting a suntan? Would the clouds stop that? Do you agree on a cloudy day? Like right now, it's sort of cloudy outside, but it's kind of sunny. But would you say that we're getting at least 70% of the light, of visible light? Well,
That's why, like, you can also get sunburn in the winter because the snow is reflecting. So
you get, if you're getting at least 70% of the visible light, you're getting at least 70% of the ultraviolet light. Which, have you ever gotten sunburn on a cloudy day?
Yes.
In fact, why do you think that is? Why do you think it's easier to get suntan or sunburn on a cloudy day? There's a reason for this. Do you think it's easier to get sunburn when you're in a boat? Anybody ever gone boating and get sunburned easily?
Yes.
Why? If you're in a boat, and you're laying in a boat in the water, are you really getting the reflection of the light coming at you? Probably not. But what's different about laying on a boat in the water versus anything else? Wouldn't you agree that maybe it's cooler? If it's sunny, what other kind of radiation is being reflected besides visible and ultraviolet? Infrared, right? If you have infrared radiation that's being reflected, it's not that hot. So you're getting ultraviolet radiation, but you're not hot. Because if you laid out on a sunny day, what's the first thing you're probably going to complain about? It's really hot out. I don't want to be out here anymore. So people go, I'm so hot, so I'm going to go inside. I'm on a lake, it's cooler, so I get burned easier because I don't think about, oh, I'm feeling really hot. Because let's face it, the first thing you feel when you're getting sunburn is you feel hot because you're getting infrared radiation. Sunburn will fry your cells at a later point, then you'll be really hot. Right? Because usually, you ever seen somebody who gets really bad sunburn? What do your friends say to them? Their friends always go, ooh, you look really red. Oh, you got sunburn, right? You don't even know about it yet. When do you start feeling the sunburn?
I feel it at night when I'm going to bed.
Yeah, you start going to bed because all of a sudden you want to put sheets over you and you're like, that hurts. Because your skin is really badly burned. Usually people can take a shower and it's like the little streams of water, just like needles. So you want to cool the sunburn of your skin, but the temperature is the infrared. That's what you're feeling throughout the day. And you're right, Shannon, in the wintertime, what part of your body gets sunburned the most?
Face.
Why?
Well, I have everything else covered.
Well, okay, that's it. You have everything else covered. But here's the thing. Here's the ground. The sun gives off radiation. Now, what do you know about the radiation coming from the sun?
Are you sharing your screen right now?
Oh, no. Well, I'm expecting that I was, but I guess I'm not. Hold on. There. So here I am on a sunny day. Now, the way that I have this drawn is that the sun is directly overhead. So if I'm laying this way, I've got really short legs. I'm laying this way, I've got my arms in the air, I'm getting my armpits all sunburned, because that would be gross. Can you imagine how horrible that was to get your armpits sunburned? Because it doesn't get a whole lot of sun most of the time, right? But do you agree that the sun is what we call directly overhead? This, what do you know about the radiation coming to us from the sun? It's parallel beam, right? But what if the sun, let me erase all these things. What if the sun, we're doing this, coming at us from the horizon? Do you see now, the sun overhead would be the radiation coming straight down. Over here, the sun is coming at an angle. So it's doing this. It's going straight down on this same angle, but you're laying flat. So the radiation hitting you is being spread out over a larger area. Does that make sense to you, what I'm showing you? So what would you want to do to get sunburn when the sun's at a lower angle from you?
Stand up.
Yeah, what you would want to do is you would either lay on an incline, and then you'd get same direct radiation, and it would be really bad. But most people don't do that in the wintertime because, like Lena's little wimp, oh, it's kind of cold outside, so I'm wearing clothes, right? You're not in your bathing suit
So
outside.
cold.
But what if I did this? What if I'm just out walking on a sunny day? Right, I'm walking. This, what part of your face, if you're looking south, it's a really big nose. There's your hat, there's your nose. Do you agree that your nose is sloped right toward the sun? And so are your cheekbones. So if you're walking, your nose and your cheekbones are giving the sun a really good angle to hit you. And you'll get as easily sunburned as you would in summer as you would in the wintertime. So really, most of the problem is just the temperature, and you got clothes that are protecting you. But you're going to get really bad sunburn because, let's face it, have you ever been to Florida in January or in December? Florida in December, people go to the beach and they get really bad sunburn. And it's really not any different. Being in Florida in December is like being here in February. Same directness of the sun. So notice all of this stuff is about being directed toward the sun based on the angle the sunlight is coming at. And this is why we're going to start dealing with seasons, because it's the shape of the earth and the directness of the sun. And that's going, boy, is that going to be a fun lecture. You're going to get mind blown, but that's how it works.
I have a question.
Yes, sir.
This might be just something that I've experienced, but why do I feel like I go up to Wisconsin a lot? Why do I feel like 75 degrees there feels like 85 degrees in like Chicago?
Well, what do you think is going to be a primary? What are the primary things besides temperature for your feeling hot? What do you think?
Humidity.
Humidity. Humidity is going to be a big one, right? The more humid it is, the more warm you're going to feel. What else?
Wind.
Wind, right? If it's windy, you don't feel quite as warm. Funny thing is, I was out walking today and yesterday. Anybody go outside last 2 days? It was windy, but it was also like a moist wind, like 32-degree dew point. Oh my God, that is just miserable. It's just bone chilling, in my opinion. Had it been drier, it wouldn't have been as bad. It just felt, yesterday and today with the wind, felt about as bad as any day that I've gone out this winter. It was just brutal. Because you're like, oh, it shouldn't be that cold. It's March, right? It's March 17th, and it was just miserable. So I think when you go to Wisconsin, it might be that it's more humid at the time, or I don't know. It's not any sunnier, that's for sure. Because the further north, the less intense the sunlight. But I think these things all the time. I think on a cloudy day, you still get sunburn. You get COVID. The disease is still going to be bombarded with ultraviolet radiation. You want to kill COVID, put it in ultraviolet radiation. In fact, have you noticed that's what some places are doing? They have these ultraviolet scans because they're trying to kill any surface stuff. That's how they clean. Ultraviolet radiation is a great disinfectant. COVID virus lasts a few seconds in a sunny day. If COVID virus takes 5 seconds to get destroyed by sunshine, when it's cloudy, it might take 10 seconds. Still going to destroy it. That's why outdoors is always better than indoors. Anyway, does that make sense? Now, I said I was going to talk to you about something. So I'm going to talk to you about, well, actually, let me pause the share. I don't need to do this. Are you guys all, am I on the screen? Are you just looking at everybody? So I got a question for you guys. You can put your pencils down because you don't need to take notes on this. How many of you believe that intelligent life exists elsewhere in the universe? Raise your hand if you believe intelligent life exists elsewhere in the universe. Aaron does,
Yep.
Isaac does, Zach, Lena, Tim, what do you think?
I'm not convinced.
Brian, what do you think?
I do not believe.
Okay,
There's
Shannon, how
something.
about you?
I believe there's like a possibility, I guess.
Okay, Sam?
I think that, with how expansive the universe is and with it expanding every day, that I would have a hard time believing that there isn't some other type of life form out there. So I do believe in any form, yeah, there's other life out there.
Okay, so, that's a different question, Sam. How many of you believe, those of you who said no, do you believe that life exists elsewhere? Life. Now, I'm not saying intelligent life, because remember, plants exist. That's life. That's not intelligent, sentient life. Do you believe that, the other guys? Isaac, what do you think? What's your reasoning behind that?
Sorry, my dog's barking right now.
Well, there's life elsewhere in your house. That's a good sign. And I
Uh,
don't think it's intelligent. I know most dogs are not that smart.
Oh, my dogs are hella dumb.
Aaron, you believe life exists elsewhere in the universe? And it's very funny because from a scientist, right? Why do people believe that? And Sam kind of elucidated that fact. Well, it's so big. It's so big. Okay. Well, do you believe intelligent life exists out there? Like sentient life, like human life that's thinking about our existence.
Aaron,
I can't say I do and I can't say I don't.
I mean, in my opinion, my own personal thing is you can believe that if you want, or you can believe not to. I don't think it makes a difference because we don't know. I mean, why does life exist in the first place would be my question. What do you think the reason for that is? Why does life exist? Why do we exist? What do you think? What's your thought on that one, Zach?
okay.
Well, I mean, there's obviously like a bunch of different like religions, for example, that give explanation to that, but like I think it's just like crazy coincidence, to like, isn't there that whole thing about like the great filter where like if we do find other life, it's like really bad for us because that means that it's common for life to happen in the universe?
Well, I mean, I guess here's the thing, right? Why does life exist? Is it some crazy chance? I personally don't agree with that. I don't, and I think from a scientific standpoint, I would say that's ridiculous. If you say God created life, well, then do you agree that it's rational to say that God could have created life elsewhere? I mean, if he did this, he could have done it elsewhere, right? That's a possibility. So there could be life elsewhere. If it came by chance, you could say, well, that's a crazy chance. Doesn't seem like it's very likely it happened twice. If it happened once, it wouldn't, but maybe, okay, whatever. Maybe it was designed to produce life. So let's imagine that. So do you think it's intelligent? I don't know. How do we find that out? I told you I was going to talk about SETI, right? Aaron, you talked about SETI. So how does SETI work? How do we look for intelligent life elsewhere in the universe? And the answer is, it's Wien's displacement law. That's why we're talking about this, because it's Wien's displacement law. So I want you to imagine that in your room right now, you have goggles on. And the goggles allow you only to see, oh, I don't know, let's go with blue. So look around your room with goggles that let you see only blue light. Like I have a very sharp filter that only looks at 0.47 micrometer radiation. What's bright in your room? Like I'm looking at Ryan's room and I'm like, his walls are bright. Lena, what is that? US, what is that poster?
Air Force.
Air Force, that's blue. Aaron, behind you, you've got like a blue shawl or something, you got a poster with blue on it.
Mhm.
Zach, looking at your room, from what I see, there's nothing really bright in there. But that's not really true, because what is white? White is all three colors, right? So if you've got white walls, there's at least a shading of blue. It may not be very bright, but you'd see it, right? Well, now, what if I said, let's float around your room, but this time put on goggles that let me see only infrared radiation? What would be bright in your room? What do you think?
Is it like similar to like how black light works? And black light like illuminates certain, I think it like illuminates white mostly.
Yeah, I mean, it certainly could, right? But no, I'm thinking not black light as much as just infrared. Things that are warm. Well, what's warm in your room?
If a light is on, the light bulb will be
maybe.
on.
Let's think about that for a second. What kind of light is warm?
Blue light.
Isn't it an incandescent light? Here, I have an incandescent light bulb. This light bulb would be like, after a while, I can't even touch it because it gets so warm, right? It's hot. And the hotter it gets, the more infrared radiation is giving off. Well, what else in your room is giving off infrared radiation? The answer is you are, right? You've all seen these movies with Arnold Schwarzenegger, what is it, Predator or something, where they put on infrared goggles. By the way, I talked to some military people, and Sam, this is kind of funny. People were saying, well, why don't you wear infrared goggles to see the storms at night? What would be really bright at night? Light, right? You shine a flashlight, you shine something warm on somebody in infrared, and it's almost blinding. It's like, whoa, that's too much. So the true military grade stop heat from generating that kind of signature. It's crazy stuff. What if you're floating around in outer space now, floating around the Earth out in orbit, and you're looking at 10 micrometer radiation? What's bright?
Stars.
Maybe, but not really. Like, what star would be bright at 10 micrometers? Well, look at the sun. But where's lambda max of the sun? 0.5. 10 is the sun would be very dark, but the Earth would be bright, right? Because it's radiating at 288. So now I'm going to share my screen. Hold on. Resume share. I'm going to go to this. Erase all this. And I'm going to say, all right, so look, lambda max is 2898 divided by 288. And that gets me 10 micrometers, right? But what if I said, put on goggles that allowed me to see only radio waves? What would be bright? Well, let's do this. What if I said I want to do 100 micrometer? What would the black body temperature be of that? It would be 10 times bigger, 10 times colder. 28.8 degrees. What if I said 1,000? Now what's it going to be? 2.88 degrees. That's 3 Kelvin, 3 degrees above absolute zero. And that's only getting me 1,000 micrometer radiation. What if I was looking for 10,000 micrometer radiation? Or 3 meter radiation like FM stations? What would be bright? The answer is the Earth is. Why? Because we generate radio waves. And if we're looking at radio waves, the Earth is bright. Why? Because that's how we communicate with each other. We give off signals. Because what in the universe is 3 degrees? And the answer is the universe as a whole is about 3 degrees. But if I were looking at 10,000, 0.3 degrees, well, there's nothing that naturally radiates energy at 10,000 micrometer radiation, or even like 3 meters or something like this. So what we do is we look into space and we have what's known as a radio telescope. Because we say we're looking for radio waves with the idea if we find radio waves, something out there must be generating radio waves. Because the only the only thing in our solar system that's bright is the Earth. Why? Because that's how we communicate. So I want you to think about this for a second. I want you to think about what are we assuming when we're looking and scanning the galaxy? How many planets, stars, would see our radio waves if they were looking at us? How long have we generated radio waves? 110, 120 years? Maybe 140 years, late 1800s, early 1900s?
They got to be only within 110 light years away.
And that's not that many stars. When you look at the size of our galaxy, that's barely touching just a handful of stars. And they would also have to be looking at the right frequency, right? Because if they were 60 light years away, they're looking back 60 years. So now we're looking at the 1950s. So people looking for the Earth would have to be looking at our TV stations, and they'd see Leave It to Beaver. And if they watch Leave It to Beaver and were able to get that signal, they go, we need to destroy this civilization because that's just we're too weird. So they'd probably come here and destroy us. But they'd have to be looking for that within a close amount of time. So the reality is, what are we trying to find? When we look out at space, are we seeing space? Not nearly as much as we're seeing what?
Space history past.
We're looking at time, right? When I'm looking at stars in the sky, every star is light that is originated at a different point in time. So when I observe the universe, I'm not observing what is, I'm observing a spectrum of time of what was. There's a whole bunch of stars that probably aren't there anymore, but they're so far away, we're seeing stuff that might be hundreds of thousands of light years away. So
Like the light from our sun, how long does it take for the energy to get from the center of the sun to the surface?
well, that's not what we're worried about. We're getting light from the outside of the sun called the photosphere. Photo means light. So we're getting light. It takes us 8 minutes and 20 seconds based on 93 million miles traveling at 186,000 miles a second. It takes 600 seconds. That's 8 minutes. Something like that, 500 seconds. And so it's a little over 8 minutes. So right now, if the sun exploded, we wouldn't know about it for how long?
8 minutes.
8 minutes. And if we were watching the sun exploding, it would have happened 8 minutes ago. But there's no way to know that because light is a finite speed traveling through space. So whatever the sun does, we have 8 minutes to find out. And once we start seeing it, we're already seeing the past. So we would have to find somebody else. Think about what has to happen. Number one, there needs to be life elsewhere in the universe. That life needs to advance to a point where there's intelligent life. That intelligent life needs to advance to a point where they will transmit using radio waves. What if they were smart enough and they could just think about each other and know what they thought, and they don't need to communicate? Or what if they're still using smoke signals or sign language, and they're not communicating via radio waves? We would never know they exist.
Yeah, we would think nothing's there.
So right now, what have we found in space? The answer is nothing. We found nothing. Although we have found radio signals, but they're things called pulsars.
And hasn't like NASA like supposedly found like an Earth 2.0 or something? I'm not quite sure.
Well, now what they're doing is we're getting so sophisticated, we can actually look at the way orbits are. We can measure the fact that orbits are slightly destructed because bodies of gravity have mass, and that mass of the Earth and the sun changes their orbits. So we can look and go, well, something's interfering with that orbit, so we assume there's planets. And then we can block out light. And there's ways of kind of interpreting that. But we are not finding any signals of intelligent life. We just won't find that. That won't exist. And we're not, and the idea, this kind of funny thing is that Carl Sagan would say, well, if we see a pattern that's not random, it must be intelligence that created that. Right? Because you're not going to get random intelligence. You're not going to get the Rosetta Stone formed by wind. Go ahead, Tim.
When we're looking for other planets, like an Earth 2.0, instead of doing the orbit thing, why don't we just look at, is there a way we can find out what the max wavelength is and like compare it to ours?
Well, that's finding the sun. The planet would be, just think about this though, right? When we see a star, we only see a few stars at night because their lights are so dim. And this is a star that's radiating at least 160,000 times more energy per unit area and is really large than a planet. So we're really not going to see, we're not going to detect a planet. What we're detecting are signals, ideas that planets would have changed certain things. Our planet will have blocked a certain amount of light from the sun. So we're seeing this idea, and then they start looking at how big are planets and how many planets can be seen. There's a lot of stuff. It's really interesting. There's great science involved, but we're not finding life. And then the question is, does life exist elsewhere? I don't know. But what do you think? Do you think that life has visited us? That would be an interesting thing, right? If the life visited us, what would they have to overcome?
War.
No. What would life have to do to overcome to see us?
The speed of light.
The speed of light. So what they do, they talk about, well, maybe we can bend space and jump across. That's called warp speed, where you're traveling fast. Because if we're traveling at the speed of light, like they've done experiments, and this, once you want to blow your mind, here's something really cool. They said, if I can accelerate hydrogen behind me, I can go faster. So if I could accelerate at 1 gravity, at 1 g, and get faster and faster, and then go half the speed of light, and then slow down, and then do it coming back, I could go to the nearest star. Do you know how long it would take me to do that? 20 years. If I could do it, if I could find a machine to go, I could get to the nearest star, it would take 20 years round trip. The only problem is when I came back, I'd be 10,000 years in the future. Because as I go faster in speed, my aging is slower. So even though I could do that in 20 years, I'd come back 10,000 years in the future. And that makes it kind of hard to do space travel. So what are we trying to do in reality? Go to Mars. Do you realize how big of a deal that would be? And that's just Mars. Going to the nearest star, yeah, that's what science fiction's about. Unless there's something where we can travel through faster than the speed of light because we bend space, it just doesn't seem real right now. What'd you say, Tim?
Like a wormhole?
Like a wormhole, yeah. So I'm just finishing up Deep Space Nine, which has wormholes to jump between the galaxies. If you ever watch Voyager, they explore a different part of our galaxy. But do you know, in the whole Star Trek Empire world, we're in our galaxy and we're only explored a very small percent of our galaxy. How many galaxies are there?
Infinite.
Billions and billions of galaxies, and there's billions of planets in each galaxy. So really, there's a big space. We're only dealing with a very small part. We're kind of small, but I think we're important. But that's my own personal faith statement. But that's how we use Wien's law, because we know that radio waves aren't going to be sent out. That's why we communicate with radio waves. And guess what? Our cells don't absorb radio waves, so we don't burn ourselves up. If we were talking in X-rays, we would kill ourselves. So we talk in radio waves, or small radio waves, and that's microwaves. But what do small radio waves like microwaves do? Water absorbs them. And when you put microwaves on water, it's going to heat it up and gets really hot, and that's why you cook. By the way, do you know what microwaves really are? Do you know where we discovered this? Little known fact. We discovered microwaves by working with radar, because we realized in World War II that if I sent out a signal, I could bounce it off an airplane and see the enemy. And they were doing all sorts of stuff. And this guy was sitting there and he goes, whoops, I had this little microwave transmitter and it melted his candy bar. And he's like, well, that's weird. And so they created microwaves to cook food because it stimulates water. And that's why we use it. And you know what the first microwave was called? A radar range. Why? Because the stuff that's inside of your microwave oven is the same thing we use inside of a weather radar to determine whether it's raining someplace. Technology and science. I don't know what's more mind-boggling, science or technology. Because science is cool, but technology does stuff. And now when you're hungry, you throw your food in the microwave. What's something that you can't put in the microwave? That's not a good idea.
Metal.
Metal, bad. What else?
Styrofoam.
What happens if you put styrofoam in there?
Like melts or something.
Maybe, I guess so. I was thinking peep,
Aluminum.
marshmallows.
Yeah.
You ever put a peep into, you know what a peep is, right? Put that in a microwave and you'll see it gets really big and then it explodes and it's a mess. Have you done that, Isaac?
I saw my friends do it in elementary school.
It's probably pretty entertaining.
Yeah.
Mom or dad may not be happy. They'll scream at you because you make a really big mess. It's another thing you shouldn't put in a microwave. It's just an egg in a shell. Because the microwaves will go through the egg. You boil, you start warming up the egg and then it gets really high pressure. And what does the egg do? It explodes. You ever cleaned up egg as it flies all over the place? It's a mess. Somewhat cooked eggs is messy. So, but those are things you don't want to do in the microwave. But we cook everything else in there, except for what? Dry stuff. Because dry stuff doesn't get hot, because why not? Like powdered stuff.
No water in them.
There's no water. There's nothing. It's not absorbing anything. It's just bouncing around and they're not doing much of anything. So you need that water. And here, I think this is cool science. What could you put in what dries out when you lose the water in it? Bread, cookies. Well, how do you make cookies less hard? How do you put the water back in cookies? You put a piece of bread in a closed container with the cookies. The bread will get really hard and crunchy and the cookies will get moist. And I'm not exactly sure why that is, but like brown sugar, same thing. Put bread in it, the brown sugar gets moist and the bread gets really hardened like a rock.
Oh, is that why, like, when you have like a piece of technology that's submerged in water, like your phone, you put it into like a bag of rice, so the rice absorbs that water?
Rice absorbs the water. Yeah, rice is
Oh
really
yeah,
cool. That's why if you go to hot, humid places like in Texas and they have salt on the table, you'll often find the salt has got pieces of rice in there because it keeps the salt from sticking together, but the rice will absorb the water. So I don't know exactly what's going on, but it's cool because science, chemistry, physics, I think they're all really cool. But anyway, that's a little bit about what we're doing. So let's talk. Let me stop the share. Let me throw you guys on my screen. Hold on. Did you like today's stuff? That was kind of funky. Next week, we have to do Earth-Sun relationships. This is going to be a pain in the ass. Can I just say that? So what's due on Tuesday? What's due for next week? You're doing more of the worksheets, chapters, right? That'll be a good place to get that done. You also have to turn in your radiation, the math lab. So fix it, put it in there, make it neat, and then I'll grade that. So I won't grade it. I won't worry about it till next week. That'll make it better, but you should have all the correct answers, right? We are going to be doing another lab next week on Earth-Sun relationships and the climate lab. So what I want you to do is I want you to print out and read through those two labs. Okay, the climate lab and the Earth-Sun relationship lab, because we'll work on that one, at least one of those in class. I do not want you to spend more than a half an hour reading through it. Just give me 30 minutes of work, please. Read it, see what's coming up, see if you go, do I know what you're talking about? And you'll go, I don't even know what the hell this is. Give us some thought, enjoy it, work on your assignments, and then Tuesday we'll start finishing up that stuff, Earth-Sun relationships, which in my mind is really boring. But I don't know how to do it, but I think we can do it together. And I think we're in a good place. So was today fun? Did you understand the stuff we did today? Kind of mind-boggling, right? Always fun to talk about the bigger pictures of science and life. Anyway, questions, comments, anything? Okay, well, listen, the sun is starting to come out, and I believe that the next few days are supposed to be sunny. And I think Sunday is supposed to be like Saturday and Sunday is supposed to be sunny. It's highs in the upper 50s.
Was it cloudy down there?
It was cloudy. It just started to break now. Yeah,
Oh,
it
it's
was
clear up here.
Oh, Sam, today was about as brutal. I'm sitting here online. It's raining. I'm doing a thing. I look at the temperature. It's 34. It's 40-mile-per-hour winds. It's raining. And then all of a sudden it started ticking as we started to get sleet. It was brutal today. What's it like up there, Sam? What's your temperature?
It's very windy. The temperature is 41.
41. So it's going to, yeah, I think over here it's a little bit better. What is the temperature here?
Probably have like gusts at around maybe 20.
It's 34 degrees out, but the sun is starting to come out. So we'll see if it gets better. And then it's supposed to be nicer over the next few days. So it's going to be a little bit more like spring again. Go Illini. Illinois is playing basketball. When they play? When? Tomorrow, Jim?
Yeah.
What time?
12:15 or something.
Okay, I'll be watching. I can't wait. I'm excited about the tournament this year. Enjoy your weekend. Have fun. Everybody gets your work's done. I'm putting in my grades, by the way, and everybody who's here is all passing, so that's all you're going to get. I don't know about everybody else, I think. But get your stuff turned in. Did you all turn in your test?
Yep.
Okay, that's all been done. So not a hard weekend. Just catch up on everything, get in good place. And then we have one more week, and then after spring break, those other labs will be due. Okay, so if you work hard next week, you won't have any assignments over spring break. It'll be due, but you can get them done before spring break, and then you can add. Is anybody going anyplace for spring break?
No.
You should. You need to get the hell out of Dodge. Anyway, enjoy life. Life's coming back to normal. We're gonna be COVID free soon. That's my plan. I'll talk to you guys later. Have a good weekend.
All right, have a good weekend.
Thank
Have a good
you.
weekend.
Bye.